Hello guys, I am Akhil. I am from Delhi, India. So I have 4 years of professional software developer experience. I specialize in delivering high quality solutions. Also, I have mentored three junior developers, guiding them through their initial phases and ensuring their smooth transition into a team. Additionally, I have led induction of numerous junior developers, fostering a supportive and collaborative environment. So today we are going to talk about the Fibonacci series. So the Fibonacci series is a sum of simple numerical series where each number is the sum of two preceding numbers starting from 0 and 1. So in mathematical terms, the sequence f of 0 equal to 0, f of 1 equal to 1, and for n greater than 1, f of n equal to f of n minus 1 plus f of n minus 2. Let's see what this means. So if we look at that, this is f of 0 equal to 0, f of 1 equal to 1. This is the default. Now f of 2 will be f of 1 plus f of 0, which will be 1. Similarly, f of 3 will be f of 2 plus f of 1. So this is 2. Similarly, f of 4 equal to f of 3 plus f of 2, which is 3. So like that, this will go on. So now let's look at the Fibonacci spiral. So it follows the Fibonacci sequence. So here we have a quarter of a circle inside a square of side of nth Fibonacci number. So here we have square of side 1 and we have this circle of radius 1 inside it. Fibonacci 1 is equal to also 1. So we have a circle of radius 1. Similarly, we have a circle of radius 2, 3, 5, 8, 13, 21, 34. So like that is increasing. So this is called a Fibonacci spiral. So let's look at the Fibonacci application in nature. So this is a shell. You can see it follows the Fibonacci spiral exactly. This is the magic of nature following perfect geometry. Even in the storms that we have, they also follow the Fibonacci spiral. See, that's how even if they are rotating, they would look even cooler. Similarly, in the galaxies, we have the Fibonacci spiral. So like that, in this galaxy, we have two Fibonacci spirals. First is this one, which is going on like, and second is this one, which is going on to the right. Even if in your face, we have a lot of Fibonacci spirals. If you see your ears, it follows the Fibonacci spiral. Even if your forehead follows the Fibonacci spiral. Like that, your mouth, your chin, your nose, everything follows the Fibonacci spiral. So now let's look at the significance of Fibonacci in the computer science. So given its simplicity, the Fibonacci algorithm makes for an ideal case study for exploring various aspects of algorithmic design and analysis in computer science. So this clarity helps grasp both recursive algorithms and dynamic programming. So let's me show you what I mean by recursion. So this is the Fibonacci implementation using recursion. So this is a Python function. This is a definition of function which takes n as input and will output the nth Fibonacci number. So if input n is less than equal to 1, we simply return n. So for 0 and 1, we will return 0 and 1. Otherwise, we will return the sum of n minus 1 Fibonacci number and n minus 2 Fibonacci number. So for example, for n equal to 2, so we will be returning Fibonacci of n minus 1, 2 minus 1 which is 1 and Fibonacci of 2 minus 2 which is 0. So it will function is calling itself. So it will call itself and n is less than equal to 1 for 1 also and 0 also. So it will return 1 and 0. So 1 plus 0 is equal to 1. So it will return 1. So now let's look at this in greater clarity using a graph. So let's say we are calculating Fibonacci of 6. So Fibonacci of 6 will calculate Fibonacci of 5 and Fibonacci of 4. Fibonacci of 5 will calculate Fibonacci of 4 and Fibonacci of 3. Fibonacci of 4 will calculate Fibonacci of 3 and Fibonacci of 2. So like this it will go on, calculating the n minus 1 and n minus 2 Fibonacci number for each n. So here you can see we are calculating Fibonacci of 4 twice. So if n was 7, so we would have been calculating Fibonacci of 5 also twice. So here a lot of computational power is wasted as we are doing calculations again and again, and it increases exponentially as n increases. So now let's look at what is the solution of this. So we will be doing dynamic programming for finding nth Fibonacci number. So how we do this is we create an array which is just a list of integers. We initialize it with 0 and 1 and we append zeros n minus 1 zeros to it. Now for I in range 2 to n plus 1, so it will go from 2 to n plus 1 is exclusive. So it will calculate first Fibonacci of 2, which is Fibonacci of 1 plus Fibonacci of 0. Then it will calculate Fibonacci of 3, which is Fibonacci of 2 plus Fibonacci of 1. So since we already calculated Fibonacci of 2, so it will use the same value. Like that, it will go on calculating up to n. So after calculating the n Fibonacci numbers, it will just return the n Fibonacci numbers. So if we look at the time and space complexity analysis, for the recursive algorithm, the time complexity is O to the power n, and for dynamic programming, the time complexity is O to the power n, O of n. The space complexity remains O of n for both the cases. So let's take an example. Let's say you are calculating the 30th Fibonacci number. The recursive method would have to perform approximately 1.7 billion operations, which is considerably slow. On the other hand, the dynamic programming implementation performs only 29 operations. You see, there is a huge difference. So here 2 to the power n increases exponentially like that, and dynamic programming increases like that. So for huge n's, it will make a lot of difference. Now let's look at the key takeaways of the Fibonacci algorithms. The Fibonacci algorithm is a numerical series where each number is the sum of two preceding numbers starting from 0 and 1. In mathematical terms, the sequence f of 0 equal to 0, f of 1 equal to 1, and for n greater than 1, f of n equal to f of n minus 1 plus f of n minus 2. So for recursion, the Fibonacci algorithm has base cases, the starting points of the sequence f of 0 and f of 1, and a recursive case which generates the rest of the series using the formula f of n equal to f of n minus 1 plus f of n minus 2. So the computationally expensive recursive algorithm can be optimized using dynamic programming. So this technique stores the result of the computation and reuses them when needed, reducing the time complexity significantly. The time complexity of recursive Fibonacci algorithm is O of 2n, which is considered poor, while the optimized version using dynamic programming has a better time complexity of O of n. Thank you.